Thin layer chromatography, or TLC for short, is a qualitative technique used to monitor the progress of a reaction, identify compounds, or analyze the purity of a sample. TLC is based upon the concept of differential adsorption, in which a compound is exposed to two competing phases. This involves a stationary phase called the adsorbent and a mobile phase, which is the solvent. The solvent is called the mobile phase because it is the component which moves up the stationary phase on the TLC plate. The stationary phase is a polar adsorbent, commonly silica gel or alumina, which are both powders that are coated onto a solid support such as glass, plastic, or aluminum plate. This process of moving compounds with a solvent is referred to as elution, and the solvents used are eluting solvents. The overall procedure is referred to as developing the TLC plate. During this process, the polarity of the sample and solvent will determine the rate at which the sample is carried up the plate by the ascending solvent. In general, nonpolar compounds travel farther up the plate compared to polar compounds because polar compounds tend to adhere to the stationary phase more strongly.
Before you begin, select a TLC plate that has little or no cracked edges. If your plate has slightly cracked edges, simply rub the edge of the silica plate very gently with clean gloves to smooth it out. This will ensure that your sample spots travel up the plate in a uniform and straight path. Next, acquire a slightly dull pencil to use while marking your TLC plate. Do not use a sharp pencil or a mechanical pencil, as this will score the silica gel and ruin the plate. Pens also cannot be used as the ink contains organic molecules that will run up the plate. With a pencil, softly draw a line about 1 centimeter from the bottom of the plate. This first line will serve as the origin, which is the starting position of the samples. In intervals of about half a centimeter, mark locations on the origin line with small ticks with an indicator below it identifying the specific sample that will be spotted there. For example, you may use the letter R to indicate a reaction mixture, SM for starting material, and P for product. Be sure to keep all spots at least half a centimeter from the edge, otherwise the samples may not move up the plate in a straight path. In addition, if the samples are too close together, they may bleed into each other and it will be difficult to tell the spots apart. Dissolve the sample in a small volume of any volatile solvent which dissolves the sample. Diethyl ether or ethyl acetate can be used for most organic compounds. Typically, for a reaction mixture, 1 to 2 drops of the mixture should be diluted with approximately 1 milliliter of solvent. For undiluted oil or liquid samples, a pipette tip of sample should be diluted with approximately 1 milliliter of solvent. Lastly, for solid samples, a small spatula tip of sample should be diluted with approximately 1 milliliter of solvent. A capillary spotter is a thin glass tube that is used to transfer a sample onto the TLC plate. Dip the capillary spotter into the diluted sample mixture. The solution should rise up the capillary. While holding the bottom of the spotter perpendicular to the plate, briefly touch the appropriate spot on the origin line. A spot of solution will form on the plate. Allow the solvent to evaporate and repeat the spot at the same location to build up a concentration of sample on the plate. If your sample is UV active, you may confirm whether you have deposited enough sample onto the plate by holding it under a UV lamp. If you see a dark spot about 1 to 2 millimeters in diameter, you have enough sample. If the samples are too concentrated, they may bleed into each other and it will be difficult to tell the spots apart. Before you begin spotting another sample, be sure to clean the capillary spotter to prevent contamination. This can be done by dipping the spotter into clean solvent, such as acetone, and depositing the solvent onto a paper towel. Do this 2 to 3 times before spotting your next sample on your plate.
The developing chamber is prepared by pouring a small volume of solvent into a beaker or jar lined with a folded piece of filter paper. The solvent level should be about half a centimeter deep. Too much solvent will cause the samples to dissolve before getting a chance to elute. Cover the developing chamber with a watch glass. Wait for a few minutes to allow the atmosphere of the chamber to be saturated with solvent vapors, which is facilitated by the soaked filter paper inside. To save time, it is recommended that the solvent chamber is prepared right before you begin preparing your TLC plate. However, do not prepare the chamber too far in advance, as each solvent in the solvent mixture may evaporate disproportionately and give inaccurate results. Using a pair of tweezers, place the plate inside the developing chamber with the origin line at the bottom. Be sure that the origin line remains above the solvent level. Immediately cover the chamber with a watch glass and allow the solvent to travel up the plate. During the elution process, it is very important that the chamber remains undisturbed. Do not move or pick up the chamber once the TLC plate is placed inside. The elution process only takes a couple of minutes, so it is not recommended that you walk away from the TLC plate for very long. When the solvent front is about 1 centimeter from the top of the plate, remove the plate with tweezers and immediately mark the solvent front with a pencil before it evaporates. If you do not mark the solvent front, you will not be able to calculate any RF values. Once the solvent front is indicated, allow the plate to dry before visualization. There are many methods of visualizing a developed plate that will depend on the sample. Common techniques include viewing the plate under UV light and staining the plate. Most TLC plates contain a fluorescent additive that allows samples to be viewed under UV light. Sample spots will appear as dark patches on greenly glowing plate and can be circled with a pencil for later interpretation. This technique is not destructive and can be repeated as many times as desired. Another method of visualizing a plate involves the use of chemical stains. This is particularly important for compounds that are not UV active. Unfortunately, staining a plate is destructive and can only be performed once. In addition, once a plate is stained, no other techniques can be used. For this reason, UV visualization should always be performed before staining. There are many types of chemical stains that allow samples to appear in different characteristic colors. An example of a chemical stain is potassium permanganate. Permanganate stains are useful for compounds which can be oxidized. Dip the plate in potassium permanganate solution using tweezers. Allow the excess solution to drip off back into the jar, and then dry the back of the plate briefly on a paper towel. The plate can be left to dry until the spots become visible. Alternatively, the process can be accelerated by gently heating the back of the plate with a heat gun until yellow spots appear. The plate should not be overheated or it will become brown and obscure the spots.
Using the spots on the visualized plate, measure and record the distance traveled by each sample from the origin line. Repeat this measurement for the distance from the origin line to the solvent front. Divide the distance traveled for each spot by the solvent front. This gives a ratio called the retardation factor, or RF. RF values should be between 0 and 1. RF values can be used to identify an unknown sample with a known compound on the same plate. For example, consider if you were required to identify an unknown sample as caffeine, acetylsalicylic acid, or acetaminophen. Since the three possible compounds vary in polarity, you could perform a TLC analysis to identify the unknown by matching its RF value to the correct known sample. To monitor the progress of a reaction, aliquots of a reaction mixture are taken over time. These aliquots are typically run on a TLC plate along with the starting material. If the polarity of the predicted product is different than the starting material, one should observe the disappearance of starting material and the appearance of product along with possible byproducts as time progresses. The reaction is considered complete once the starting material is no longer observed. The purity of a sample can also be analyzed by examining whether or not a sample spot is accompanied by additional spots. A pure sample will only show one spot. However, an impure sample will highlight contaminants as additional spots in the same lane.
To briefly review, in performing TLC, samples will first be spotted on a TLC plate. The plate will be developed in a developing chamber with an appropriate solvent. Once eluted, the plate needs to be visualized. Common visualization techniques include UV light and staining. After the plate is visualized, interpreting the plate is done by comparing RF values.